AGC chemicals, and he's going to talk to you about fluoropolymer coatings for bridges.
Thank you, guys. I appreciate the opportunity to speak to you guys. My name's Winn Darden. I work for a company called AGC Chemicals. We make a raw material for long life coatings. So we don't make paint. We sell to manufacturers of paint. Our product is the key ingredient in these materials. I'm going to talk today about fluoropolymer coatings for bridges and a little focus on corrosion resistance today. Just before I get started, I changed barbers a couple of weeks ago. I went from a guy, had like 4 or 5 chairs, a small place, and I went to a big new place that's got mirrors on both walls, and they got 8 chairs on each side and everything. I went a couple of weeks ago, and the barber kind of moved aside. I'm looking at my reflection in the mirror and everything. He kind of moves aside, and I glance up there, and I say, wow, that guy, there's a guy over there. Look at the size of the bald spot on that poor guy's head, right? And then I go, oh no, wait. So one of the things about getting older, I guess, Rogaine won't do me any good these days, I don't think. So I'm going to talk about what are FEVE fluoropolymer coatings. I'm going to define these and give some of their physical properties. We'll look at some conventional corrosion testing, and then we're going to look at electrochemical impedance spectroscopy, or EIS. We've done some testing on fluoropolymer top coats. Also have a little bit of information on rapid EIS testing for coatings. A couple of coating specifications and a life cycle cost analysis, and then some of the applications, just some photos of bridges in the U.S. that have been done with these materials. So what are these products? Well, we call them FEVE, or fluoroethylene vinyl ether. There's nothing really complicated about that. It's we take the raw materials that make up the polymer, and we use those abbreviations. So it's fluoroethylene vinyl ether. We take a fluoroethylene material and we take a vinyl ethers and we polymerize those. We make a plastic out of those, basically. And what we can do with this is we can make these materials soluble in solvents and compatible with water. We can make solid materials by removing solvent. If you think of something like Teflon, Teflon is the fluoropolymer most people are familiar with. Teflon doesn't dissolve in solvents. It's very difficult to work with in water. If you want to use it for a coating, you basically have to melt it. And the temperatures that these pure fluoropolymers melt at are very high. So it's not practical to do that. What they've done with this, what our company has done, is they've made a fluoropolymer. They can take advantage of some of the properties, but they can also make a product that you can make a paint out of. And this was really the second product that came along that you could do that with. So what do these things do? Well, these have excellent weatherability. These materials can give a top coat life of 30 plus years. There are bridges in Japan that are painted with these materials. The life of the bridges are estimated at around 120 years. They want to paint it one time in that 120-year life cycle. These can be shop or field applied. So you can use these either for new construction or you can use them for rehabilitation in the field. The products use standard painting equipment and application method. No special equipment required or anything like that. The products can be, our customers formulate these products into materials that can be used anywhere in the U.S. as far as VOC or solvent regulations go. They have superior gloss and color retention, resistance to chalking or fading. They resist acid rain, airborne chemicals, solvents that are used to clean graffiti off bridges, and they have good corrosion resistance. When we look at weathering in the coating industry, we look at a couple of different types. We look at accelerated weathering, which is basically exposing coatings to high energies of ultraviolet radiation, and then looking at, in this particular case, gloss retention. The gloss retention is kind of a proxy for the degradation of the coating. So what you want is as small an amount of gloss loss as you can over the life of the coating. And you can see here in this particular case, they've run this out to 5,000 or 6,000 hours. You can see the FEVE coating on the top line. It has the best gloss retention. Polysiloxane is pretty good. The polyurethane, which is the most commonly used coating in the bridge industry, I think, does not weather particularly well. We also look at real-time weathering. That's where the rubber meets the road, I guess, is in that. And here what we've done, we've tested this in South Florida. So they have exposure cabinets and panels that they load panels onto these racks, and they put them south-facing, usually at 45-degree angle. And then over time, they look at gloss retention. And we pick gloss retention because it's easy to measure. There are instruments you can take out in the field and measure with it. So it's an easy way to measure degradation. And you can see here what the gloss retention of the two FEVE coatings is very good after 10 years in South Florida. Some more real-time weathering, this time looking at chalking. What they've done is they've set up a platform in a bay in Japan, and they put panels on the racks on the platform, and they can look at they'll look at, for example, different alloys. How do those hold up in a harsh environment like that? They also look at coatings with that. And again, what they're doing here is they're measuring the amount of chalking that's occurring on the surface of the paint. If you paint your house and you go out 2 or 3 years after you paint it, you rub your fingers on it, it'll come off on your fingers. And all that's the polymers that are in the paint breaking down. So those are lower molecular weight. Rain and wind will usually take those things away, but that's an indication that the coating is degrading over time. There are standards. What they do is they compare the chalking on these test panels with the standards, and what you see is after about 10 years, the polyurethane is completely chalked. If it's, say, a red, that means the red will be faded. It might even be trending toward pink at that point. Whereas the FEVE coating after 20 years in this environment shows very little degradation. The reason people use coatings on bridges is really for corrosion resistance. Appearance is nice. You can have bright colors on bridges. There's a call for that. In most cases, people are using a 3-coat system consisting of a zinc primer, usually an epoxy middle coat, and then a urethane or polyurethane top coat. And there are variations on that. You can do 2-coat systems and things like that. But primary corrosion resistance in those systems is provided by the zinc primer. So if the coating is damaged, what happens is the zinc corrodes preferentially to the steel. And usually you'll have some indication that you have damage and corrosion. There'll be a gray spot on the surface of the coating that'll indicate that, the primer is degrading. That spot needs to be touched up before degradation happens. What the top coat is really doing, it's not only providing the appearance you're looking for, but it's keeping corrosion initiators like chloride, water, and oxygen from reaching the metal surface. So these FEVE top coats are superior in their longevity. So it seems logical that if they retain their coating thickness over long periods of time, they'll be a more effective barrier against these corrosion initiators. So this is one of the tests we run. This is the ASTM salt fog test. They take these, in this case, it's a 5% salt solution. They run it for 2,000 hours in a testing cabinet where they spray the panels with the salt. And what they do before the test is they scribe the coating. They scratch the coating down to the metal surface. And then really what you're looking for is rust in the scribe. How much did it rust? And then you're looking at how much does it undercut? How far does it go under the coating? In a car, for example, if you damage the coating, you'll be able to. You may start some rust in the area that's damaged. But what they're really good at, and by treating the metal, what they're really good at is keeping that rust from moving under the coating. So that's something the automakers do pretty well. In this particular case, what they're looking at polyurethane and a polysiloxane. And visually, you can see there's less rust in the scribe from the FEVE coating than there is in the urethane and the polysiloxane. They did not look at movement under the scribe or blistering under the scribe in this particular test. There's another test that's run called Cyclic Prohesion. And what they do in this test is they alternate exposures. So they'll put the they'll put the coated panels into a weathering chamber for a certain amount of time. Then they move it into the corrosion chamber. Again, they scratch the panels so that you're going to get rust in that scribe. And they move this back and forth until you get about 5,000 hours of total exposure. And what you're trying to do here is that how does the corrosion resistance of the coating, how does the coating perform after it's been exposed to weathering? So in other words, to ultraviolet light that's starting to break the coating down. And you can see in this case, they've looked at a 2-coat and a 3-coat system. And they looked at organic zinc, urethane, and then a polysiloxane, and then the FEVE or fluoropolymer material. And they measured then how far the rust penetrated under the scribe. 8 is a pretty good result for that. It's not, you'd like to have that as low as possible, but that's not a bad result for that. So you can see in both systems, the FEVE coating is equivalent to or outperforms the other coating products. One of the things to notice here is they measured gloss retention here, and you can see the comparison between the other 2 coating types and the FEVE coating. The gloss retention is much better in the FEVE coating. This is just a couple more tests. The ISO 12944. ISO is pretty widely used in Europe and Asia, and it's gaining more acceptance over here. There are more people who are looking at this. This particular standard deals with industrial maintenance coatings, and they run a couple of tests here. One of these is running it under highly corrosive environment. That's the first smaller table there. And in this particular test method, all of the materials pass. The second test is actually an immersion test. We usually don't use these materials in immersion, but what you can see here is that the 3-coat system does pass that immersion test, and you don't get much cathodic disbondment. In other words, the coating, if you have a cathodic protection on a metal substrate, the coating is not going to delaminate because you have cathodic protection on it. And then, what is that? Yeah, they tested in seawater immersion, and it passes as well. The first 2 test types, what you're doing here, you're scribing that coating. So what you're really testing is the efficiency of the primer at preventing corrosion. What we're interested in is we're trying to find out what does the top coat contribute to corrosion protection. Not the primer. What does the top coat contribute to that? That's a lot harder to figure out. So there's a test called electrochemical impedance spectroscopy, or EIS. It's being used more widely now for corrosion testing. What you're doing is applying an AC voltage to a coated metal panel at different frequencies. You're measuring the current. You fit that raw data to various electrical models, and you can progressively monitor the change in impedance over time. What you're hoping for is that the impedance stays very high over the life of the coating. We can measure top coat performance. We can put the coating directly onto the metal surface. So now we can measure only how much that top coat is contributing to the corrosion resistance. It allows you to quickly assess changes in coating formulations or surface treatments. It's kind of the first one test you'll see is not really that short a period of time. The second one is. So I'll talk about 2 of those. It's also a non-destructive evaluation. In other words, you're not scratching the coating or destroying the coating. You're looking at what does the undamaged coating do to prevent corrosion. You can monitor corrosion, and you can also monitor things like water absorption in the coating. So this is kind of what you're looking at. The electrolyte is the water or salt water you're exposing the panel to or the coating to. There's going to be a corrosion reaction at the metal surface, and then you've got the metal itself. So it's a fairly complex thing that you're seeking to measure with EIS. Here's the apparatus. It's they use a silver electrode. They use a graphite rod as the counter electrode. They start at a initial frequency, and then they change the frequency over time, and they'll get graphs that look at this over the changes over the frequency, over the life of the coating, the changes in frequency. And here they looked at a 0.5 molar solution of sodium chloride. They're looking at aluminum here. When you start to look at steel, it gets a little more complicated. Steel is going to show corrosion more than that. We are looking at that in the lab now, and that's kind of like what's the best method we can come up with that's going to test the top coat on steel. So it's a little more complicated than just slapping the paint on there. There are a couple of different things we can do. We can do a Bode plot, which is on the left, and that displays the frequency response with impedance. The Nyquist plot is a plot of imaginary versus real impedance and the capacitance effect. What you're really looking for in Nyquist is that the y-axis is a perfect capacitor. So you want your over the exposure time, you want your coatings to be as close to vertical as you can. You want those readings in that graph to be as close to vertical as you can get it. Here's an initial impedance run for these three different coating types: the fluoropolymer, FEVE, polysiloxane, and polyurethane. Anything over 10 to the 8th ohms per square centimeter is considered to be corrosion resistant. So all three of these coatings initially offer very good corrosion resistance. Here's the Nyquist plot after a 50-week electrolyte soak. I like this. I think it's easier to see the performance of the individual coatings. What you're doing here is if you look, you have to do this at 0.1 ohms per centimeter, and if you look at it, it's kind of difficult to tell that. You almost need a computer to do the readout. You can't do it manually. Here, I think visually it's easier to see. Again, we want to be as close to vertical as we can, and you can see the FEVE coating does that. The polyurethane is pretty good as well. The polysiloxane, surprisingly to us, it looks like it's not performing as well. So we did 50-week soaks. Well, you saw the results, and then 120-week soaks, and then we stopped the test. You can see here that all initially were good. All are over that 10 to the 8th after 50 weeks, but after 120 weeks, the polysiloxane falls below that. Again, interesting results for us. This is kind of graphically looking at the same thing, looking at retention of impedance, or how little does the impedance change over time. And you can see here it's a little bit easier to see the change in impedance over time. And again, the urethane, since it's over 10 to the 8th, it does have good corrosion resistance. There's another technique we can use called rapid electrochemical assessment of paint, REAP, using EIS. This is a short-term test, and you can estimate corrosion results. You can get initial impedance, you can get water uptake, and the corrosion resistance of the coated steel. We did this on a powder coating initially, and one of the things we wanted to do this because you'll see in the next slide the powder coatings have some properties that make the contrast between a good coating and a not so good coating a little bit easier to see. In a powder coating, what they're doing is the ingredients of the paint in a powder coating are all solid. There are no solvents or liquids or anything. You're blending these materials together. You spray them on a charged metal substrate. They adhere to that, then you put them in an oven, and they cure when you put them in the oven. So it's a little bit different than a regular paint. The parameters, what you're looking at is what influences the properties of the coating. Well, certainly the feed rate does. In other words, how fast is that powder moving through? The formulation chemistry, obviously the paint itself is going to have an influence on that. You can do different barrel zone temperatures as this material is going through the barrel of the processor. You can raise or lower temperatures. You can change the mixing and things like that. Screw rotation, RPM, affects the residence time. And the screw profile gives you better dispersion under certain conditions. So this one focused and changes on rotation and residence time. We just picked two of those and ran with that. If you look at the pictures, the one on the left-hand side, even though the surface of the coating is not perfectly smooth, this had a faster screw rotation, so a shorter residence time, an increase in temperature. You reach the glass transition temperature, or in this case, where the solid material moves into a liquid form and starts to flow. So what you have is you have a smoother coating with fewer defects on it. If you look at the one on the right with this screw rotation, you can kind of see the little holes in the surface, and this is created because you're getting poor surface quality and you're getting defects in the coating. Well, when you have a defect in the coating, this can let those corrosion initiators come through. So that's the reason we kind of did this first on powder, because it's a little bit easier to see, and there's more of a contrast between the two. Again, we exposed the sample to this sodium chloride or salt solution. We looked at impedance over time, measuring water uptake in this particular case. We calculate that from the impedance. We contrast here the higher RPM in the first row and the lower RPM in the second row. And in this particular case, you're looking for water uptake. And what you see is that the higher RPM gives you less water uptake. That should correlate to the corrosion resistance of the coating. In other words, a coating that does not have any surface defects or pinholes is going to give you better corrosion resistance. So you can see here there's a lot of different things you can do with this technology that make it kind of an exciting tool for us in the coating industry. Real quick, just some coating specifications. The 260, this is the old SSPC and NACE have merged together. This is a fluoropolymer coating standard that was produced year before last. So if you want to specify these materials, you can get this standard, and it'll give you the physical properties and should enable you to spec the coating. This particular spec is from the Iowa DOT. This is it's a new bridge over the Mississippi River in the Quad Cities area of Illinois and Iowa. So I think this opened last year to traffic. So the fluoropolymer top coat was used in this, and it was shop applied with field touch-up. Case study, this is a bridge in Japan. This was coated in 1986, and they looked at it for 30 years. They looked at the different properties of the material. And what you can see here these are photographs of the bridge over the 30-year period. If you look at the color change, which we call delta E, and if you look at the gloss retention of the cleaned, or after wiping especially, because the dirt does accumulate on these things, you can see it's outstanding color retention. Anything less than 5 on the color side is barely discernible to the eye. And the gloss retention after that 30 years is also excellent. So good indication of the long-term performance. A couple of projects that are ongoing right now. This is the Sunshine Skyway Bridge is being repainted. The steel casing for the cables is being repainted with an FEVE coating. Obviously, a bridge like this, it's really difficult to shut something like that down on a regular basis to repaint. So what they want to get with this is something that's going to be out there for 20 or 30 years. They're not going to have to mess around with repainting the surface. This one was just completed this year. This is the Cold Spring Canyon Bridge. Caltrans in this one specified a water-based coating that was made with one of the FEVE resins. The project was completed this year. This is, I think, the highest arched bridge in California. Last but not least, I risked my life to get these pictures. I was on the 101 freeway and snapping pictures out the rental car window, so I did not wreck the car, so I'm very proud of these, actually. But these are two viaducts, the Bayshore Viaduct and the Central Viaduct in the San Francisco area. And they're repainting these with a standard Caltrans coating. They call it Coronado Blue. So the indication is that's what the Coronado Bridge in San Diego is painted this blue color. So that's the next step with this. We're going to put this on the actual bridge it was named for. But again, it is being used in this is a water-based coating again. It is being used on this is quite a project. There's actually another one in Sacramento at the Interstate 5 Route 50 interchange in Sacramento is also being done. That one in a green, not the blue. So that's it. Sorry if I went over. Thank you, I appreciate it.
The preceding was produced by the National Center for Pavement Preservation. More information can be found on the web at pavementpreservation.org. Additional support provided by Michigan State University.